free body diagram of rotating body in 3D. So let's imagine that there is a rotational axis, but now we are going to analyze the real case. So axis become to rod. The rod, this is rotational axis, realized as a rod, and this rod is supported in two places, A and B. So there is rotational joint, and on the other side there is rotational joint too, like this. Okay, so let's denote it A and B. We have two rotational joints. There is a body on this rod. The body is a very general case of a body, because let's say that, for example, center of mass is somewhere in the space, in the volume of the body, and let's say that C is a center of mass with position defined by coordinates xc, yc, zc. So it is a position of center of mass of body. Let's say that we know mass of the body. We know moment of inertia Jx. About x-axis, and we will make this axis, the equal to O. So this is x-axis of coordinate system. We know dxy, dxz, so cross moments of inertia. And I will add something in a minute. So if we are talking about x, y, z coordinates, so we should define other two directions of y and the z axis. So let's say that somewhere in the space is a origin of coordinate system. So let's say that this is y-axis and this is z-axis, and this is 0, or as an origin. Okay, and this is x-axis. So we have a coordinate system x, y, z. Let's say also that if we expect that the body rotates, so there should be some exciting moment, some external moment. So I will add it. So it is denoted as a vector m external. Okay, so using a right hand rule, I use right hand. I have my thumb oriented in the same direction as the vector of moment, and my fingers denotes the direction of rotation. So this body is accelerated by this moment in this direction of rotation. We should also know this topology of the system. So I will make these dimensions So there is L1 and L2. So L1, L2 are dimensions. And now I think it's totally definite task. And I mean given values of task. And task itself is calculate dynamical forces, we mean reactions in joints A and B. So let's imagine, I think it's quite practical axis task. You have a rotational axis, some rod with two rotational joints, and you have unbalanced body. Why it is unbalanced? Because the center of mass is not on axis. Okay, so some dynamical forces will be generated here, and it has also some non-zero non-trivial cross moments of inertia. You will understand it later. So if we start to rotate this body, the dynamical forces will appear here. So we are going to calculate them. So first, what we need to do when we solve some dynamical tasks is to draw free body diagram, and I will use this image for this. So reactions are in these joints, so there will be a component of reaction R, A, Z in Z direction, and also there will be a Y component R, A, Y, and because there is also constraint this motion, I will add RAX. Similar situation is here in this joint B, so there we can expect RBZ, and in this direction RBY. There will be no X component of B because there is no this sliding constraint. So it's a usual technical solution. But these green forces are only reactions. And what about action forces or dynamical forces? The only action force is here. In fact, it's a moment. And into free body diagram we also need to draw dynamical forces as we derived previously. So when we draw, I will make some comment here. In free body diagram, we draw action forces or like forces, so it's external moment, reactional forces, RAX, RAY, RAZ, BY, RBZ, and dynamical forces if we use D'Alembert's method. So what are the dynamical forces? First, it's D'Alembert force. We can draw it as a normal and tangent component. And following the theory, we need to find a projection of point C to this plane YZ of coordinate system. So there is C with prime, and C with prime is a projection of so it's a projection of center of mass to plane YZ of coordinate system. Okay, and we will use this projection for positioning of O force. So there is O force, it's normal component of D'Alembert force, and perpendicular to this, against direction of rotation, there is tangent force. Okay, so there is C, projection of C in this plane. And another kind of dynamical effect, it is D'Alembert's moment. So it is MD, and it is composed from MDX, MDY plus MDZ. So we are going to draw these moments into free body diagram. So we follow the position of coordinate system and we draw three moments: MDX, MDY and MDZ. And now that's all. I think there may arise a lot of questions. It's not so easy, but in fact, once the complicated theory is derived, once this is derived, we can use it as a pattern. We only replicate. So it's not so complicated, and if you have any question, please ask me by email. So now it's completed. The free body diagram is completed. Let's notice that all dynamical forces are placed into the origin of coordinate system. And now I am going to say something very important. The most important property of solution or feature of solution is a coordinate system. If we have a body, we place somewhere the origin of coordinate system with axis x, y, z. In this coordinate system, we reach by integration jx, dxy, dxz, and into this coordinate system from which we derive these values. So to this origin of coordinate system we place the beginning of vectors of dynamical forces. So let's go to set the equations of dynamical equilibrium. So because it is three-dimensional case, we will have 6 equations. 1, 2, 3, 4, 5, 6. First three equations will be component equations in direction x, y, z. Second three equations will be moment equations, so around x, around y, around z. So let's start to make it. You will not see directly, what's a bit pity, but let's see the all forces in x direction. So definitely it's not ME, it's not a force, it's a moment. It's a force effect, but not force itself. So the only force here is reaction force RAX. No other force is here. So I am writing RAX is equal 0. And to don't confuse you, as I told that moment is not a force, really it's not a force, but force effect. If we have two forces, it can make moment. Okay, but moment is not force, so action, force, effects, let's say, okay, not forces. And what about y direction? There is RAY, RBY, and there are some components of O and T projected to y direction. We need some angle here. Let's see, what is this angle? Let's say beta. Okay, this is the same angle as it is here, beta as well. Okay, so we will calculate it later and we will use it now. So I am writing that it is RAY plus RAB plus O by cosine beta plus T by sinus beta. What about z direction? There is RAZ, RBZ, and Z components of O and T forces. So I can write that it is RAZ plus RBZ. There is a mistake, so it's RAY. There should be Y. Plus O by sinus beta minus T cosine beta is equal to 0. So three component equations of forces are completed, and now we are going to set up three moment equations. So let's see which moments are acting around axis x. So there is ME as an action moment and MDX as a reaction moment. So we can write that MDX plus M external is 0. What about moments about y-axis? So we have RAZ on L1 rotating around y-axis. So this is RIZ by L1, and if we consider that it is negatively oriented moment with respect to right hand rule, it doesn't matter, but it's some rule only. Second reaction is RBZ, and it's positively oriented and it rotates in direction it makes moment on displacement, yeah, on displacement L2. And finally there is a moment mdy rotating about y-axis. So that's all. And what about moments or forces about z? So there is a moment r a y on L1 length minus r b y on L2, and finally mdz is equal to 0. And this is almost all. We have 6 equations of motions, one motion, and which unknowns we have here. We could make an analyze, but we need to add some more equations. So I can write additional equations. So 7th equation. What about b? How to calculate beta? Sorry, not b, but beta. We can calculate this angle beta from position of center of mass, because this is ZC and this is YC. Okay, so tangent beta is ratio ZC and YC. From that we can calculate beta directly. Also we can define 8 what is a normal component of D'Alembert force. So it is ma omega square. It's a normal component of D'Alembert's force. What is a? It's a this displacement, this length. So when I leave blank one position, so I can add that E is yc square plus zc square, and I left blank place for t. It is from definition me alpha. 11. mdx from the theory is minus jx by acceleration, angular acceleration alpha. 12. mdy is from theory alpha dxy minus omega square dxz. 13. From theory mdz is alpha dxz plus omega square dxy. And there are also some kinematical dependencies. So alpha is d omega over dt, and we will use it later. 15. Omega is d phi over dt, but at this time we don't know what is phi. We will know it later. Now we have enough equations for calculation of reactions. So finally we are going to calculate Rx, Ra, Y, Ra, Z, Rb, Y, Rb, Z, and maybe other quantities we can calculate as well. So let's say also that we will use a condition of that motion that, for example, external moment is equal 0, so it's free rotation. It was rotated to some velocity and we cancelled the external moment, and now we are investigating the reactions. So we can calculate these values from that system. It's not so complicated. So yeah, the simplest one, Rax is equal to 0. It follows from first equation. But other reactions, Ray or Rayz, will be functions of many values, but also functions of omega and alpha, and like this. Function 1, function 1, function 2, omega alpha. So if I have this axis, this origin of coordinates, this is y, this is x, and this is z. So I get components regarding this coordinate system. So if I use this coordinate system, y, z, I can find here, for example, reaction Ray and Raz. And I can find resulting reaction Ra. So Ra is Ray plus Raz, and if I need to know this angle, for example gamma A, so I can say that tangent gamma A is a ratio of Raz over Ray. So from this follows gamma. So it seems in this coordinate system zero, x, y, z, Ra is constant. But we must notice that this coordinate system is a local coordinate system. Connected with body. So this local coordinate system is rotating with body because it is system connected with body. But there is also global coordinate system. So we have system xg, yg, zg. This is global coordinate system. Connected with ground. So I can denote it like this. So there will be some global coordinate system connected with ground, and regarding this coordinate system, the local coordinate system is rotating. So this is our phi. So we can transform this to global coordinate system. There is y, g, z, g, while gamma a is constant, then phi is changing with rotation. So we can say that r a, let's say, RA in global coordinate system is RA. We can leave it blank or we can write L here by cosine, cosine gamma A plus phi, and it will be Y component, and RA global Z component is RA by sinus gamma A plus phi. So if we draw some individual component, for example R, A, Y in global coordinate system, there is Y, G, there is Z, G, we will get some sinus or cosine function, and this makes vibrations. So the same picture we can draw for this part of reaction for other reactions. So now maybe we understand that body, rotating body, where center of mass is not fixed to axis of rotation, and there are some cross moments of inertia generates dynamical forces which makes vibrations, and these vibrations are dynamical effects of unbalanced bodies.